Starting off, we have square and rectangular matrices. Square matrices have the same number of rows and columns, forming a perfect square. In contrast, rectangular matrices have a different number of rows and columns. An identity matrix is a square matrix that has ones on the main diagonal from top left to bottom right, and zeros everywhere else. It's special because multiplying any matrix by the identity matrix gives back the original matrix. A square matrix where all elements above the main diagonal are 0 is a lower triangular matrix, and on the other hand, a square matrix where all elements below the main diagonal are 0 is an upper triangular matrix. A diagonal matrix is one where all non-diagonal elements are 0. The identity matrix is actually a special type of diagonal matrix where all diagonal elements are 1. Before we continue, let's quickly review the transpose of a matrix. The transpose is obtained by swapping the rows with columns. For example, if we have this matrix, its transpose would be something like this. The rows and columns got swapped. Note that the transpose is denoted by the letter T. This will be useful in understanding some of the upcoming matrices. A symmetric matrix is one where the matrix is equal to its transpose. A quick way to identify this is by checking if A of ij is equal to A of ji, where I denotes the row and j denotes the column. A skew-symmetric matrix is one where the transpose is equal to the negative of the matrix. One important property is that all diagonal elements must be 0. An idempotent matrix is one when no matter how many times you multiply it by itself, the result is always the same matrix. And something closely related to it, we have a nilpotent matrix, which is one where no matter how many times you multiply it by itself, the result is always a 0 matrix. An involutory matrix satisfies this condition. This means that on multiplying the matrix by itself once gives the identity matrix. To understand the next set of matrices, we first need to define the conjugate transpose, also called the Hermitian transpose. A conjugate of a complex number means flipping the sign of its imaginary part. So the conjugate transpose means taking the transpose after applying the conjugate. So let's say we have this matrix here. We'll take the conjugate of each element, and now we'll transpose it. As you can see, we got back to the original matrix. So this is a Hermitian matrix. The conjugate transpose is denoted by the letter H. Similarly, we have a skew Hermitian matrix, and you must have guessed it, this satisfies this condition, meaning its conjugate transpose is the negative of the original matrix. There's one important matrix we haven't covered yet, the inverse matrix, and it involves a separate video for itself, which I'll be bringing to you soon. So stay tuned for that, and I'll see you in the next one.